Welcome back to the Deep Dive. Today, we are doing something a little different. Usually, we take a topic and we drill down. We go microscopic, we look at the details of a business deal or a specific historical event. But today, we are going the opposite direction.
We are zooming out.
We are zooming way, way out.
To the absolute limit of what we can see, really.
Exactly. We are
Wow.
tackling the universe, the whole thing. And we're basing this conversation on Astronomy, a Visual Guide, which is this massive, beautiful compendium of, well, everything. And I have to be honest, when I first opened this source, I was expecting a lot of star charts and, Latin names.
And there is some of that, to be fair.
There is that. But the very first concept it hits you with is something much more, I don't know, psychological.
It franks the whole science differently, doesn't it? Right from the first page.
It really does. It starts with this idea of the time machine.
Hmm.
The text says, a casual glance at the sky transports us across gulfs of space and time. And I think we need to stop there before we get into any of the physics. Because when I look up at the night sky, say I'm out camping far from the city, I see points of light. They feel present. They feel like they are there right now, shining on me.
Of course.
But that's a complete illusion.
It is the ultimate illusion. And breaking that illusion is really the first step to becoming an astronomer. You have to internalize the speed of light. Light travels incredibly fast, 300,000 kilometers per second. But space is just so unimaginably big that even light, it crawls by comparison.
It's the cosmic speed limit, but it's still the speed limit.
It is. So when you look at the moon, you aren't seeing the moon as it is this instant. You're seeing it as it was 1.3 seconds ago.
Which is negligible. That's like a bad video call lag.
Sure. It's almost real time. But then you look at the sun, and please don't actually look at the sun, but the light from it.
That's 8 minutes ago.
8 minutes in the past. If the sun vanished right this second, we wouldn't know about it for 8 full minutes. We'd still see it shining. We'd still feel its gravity pulling us in our orbit. Complete blissful ignorance for 8 minutes.
It's just a strange thought. But that's just our front yard.
Exactly. Go further. The source brings up the Orion Nebula. Everyone knows Orion, right? The hunter in the winter sky.
The belt is the easiest thing to spot. 3 bright stars in a perfect row.
Right. And hanging from that belt is what looks like a sword. If you look closely, even with your naked eye, the middle star of that sword looks a little fuzzy. It's not a sharp point.
Yeah, I've noticed that.
That is the Orion Nebula. It's this vast cloud of glowing gas and dust. And the light hitting your retina tonight left that nebula 1,500 years ago.
So just to put that in context, that's roughly around the fall of the Western Roman Empire.
Precisely. That light has been traveling through the void while entire empires rose and fell, while the printing press was invented, while we crossed the oceans, while the internet was created, just to land in your eye tonight.
That's amazing.
But here is the kicker. It's not just about the delay. It's about what that delay lets us see. Inside that nebula, if we point a telescope at it, we see brand new stars being born. It is a stellar nursery.
So we are watching a reenactment.
We are. It's a replay. We are seeing a live broadcast of what our own solar system looked like 4.6 billion years ago. We can't see our own birth, obviously, but we can look out across the galaxy and see other stars going through that exact same infancy.
That is a wild thought.
Okay.
So by looking at different objects at different distances, we are effectively looking at snapshots of our own life cycle, a sort of cosmic photo album.
That's a perfect way to put it. You look at the Pleiades, the Seven Sisters, that beautiful little cluster of blue twinkling stars.
They look like a tiny little dipper.
Yeah, they do. And those stars are teenagers. They're young and hot. They formed around the time early human ancestors were just starting to walk upright on Earth. They are fresh. Then you look at something like Betelgeuse, the bright orange-red star in Orion's shoulder.
Can't miss that one. It's so red.
That is a dying star. It's a red supergiant. It's old. It's showing us our sun's distant, distant future.
The source mentions Betelgeuse is destined to explode. That sounds pretty dramatic.
It is. It's distended is the word they use. It's swollen up to a massive size. If you put it where our sun is, it would swallow Earth and Mars, maybe even Jupiter. And it's burning through its fuel at a furious rate. When it finally goes supernova, it will be visible in the daytime sky on Earth. It'll be spectacular.
And what happens after that? After the big show?
Well, the beautiful part, the part the source emphasizes, is what happens next. It says the explosion will spill its constituent atoms into the interstellar mix.
Recycling.
Cosmic recycling on the grandest scale. The carbon in your cells, the oxygen you're breathing right now, the iron in your blood, all of that was forged inside a star like Betelgeuse that lived and died billions of years ago.
So we are literally stardust. That's not just a poetic phrase.
It's a physical fact. We aren't just looking at the universe. We are made of it.
Right.
We are a way for the universe to know itself.
So the mission for this deep dive, then, is to shift that perspective. We want to move from seeing the sky as this static wallpaper of unchanging lights to understanding it as this violent, dynamic, evolving engine that created us. And to do that, we have to go back to the beginning of human understanding.
Back to a time before we even knew what stars were.
Exactly. Let's start with the accountants of the sky, the Babylonians.
Right. Modern-day Iraq. The Fertile Crescent. We're talking around 700 BCE.
I found this section fascinating because I always associate ancient astronomy with the Greeks, with philosophy and geometry and models of the universe. But the Babylonians were doing something arguably more practical, more foundational.
Oh, they were the bureaucrats of the heavens.
Yeah.
Data hoarders. They weren't necessarily trying to build a physical model of how the universe worked. They just wanted to know when things would happen. It was all about prediction.
So they kept records.
Meticulous records. They kept these clay tablets lists and lists of observations stretching over centuries. The MUL API tablets are the most famous examples. They're basically an almanac. They list the rising and setting times of constellations, dates for solstices, eclipses.
And what's incredible is that we are still using their pictures, their constellations.
We absolutely are. If you look at those ancient tablets, you see a lion, that's Leo. You see a scorpion, that's Scorpius. You see a bull, Taurus. These cultural images, these patterns, have survived for nearly 3,000 years, passed from Babylon to Greece to Rome, and eventually to us. It's an incredible chain of knowledge.
The thing that really blew my mind was the math. I've always wondered, why is a circle 360 degrees? Why not 100? Or 1,000? It seems so completely arbitrary.
It seems arbitrary to us with our base 10 thinking, but it's pure Babylonian. They noticed that the sun takes roughly 360 days to complete a full circuit of the sky a year.
It's actually 365 and a quarter, but they were close.
They were close enough, and 360 is just a much, much nicer number to work with.
It's so divisible.
Highly divisible. You can divide it by 2, 3, 4, 5, 6, 8, 9, 10, 12. I mean, the list goes on. So they mapped the path of the sun into 360 degrees, with each degree representing about 1 day's movement.
And they didn't stop there, did they? They gave us the hour.
That's right. They used a base 60 number system, again, probably because 60 is so divisible. So they took that degree and split it into 60 smaller parts, which they called minute parts from the Latin for small, and they split those into 60-second parts.
So every time you look at your watch and see 60 seconds in a minute, 60 minutes in an hour, you are using Babylonian math from almost 3,000 years ago.
That is their legacy right there on your wrist.
But for them, this wasn't really physics, was it? It was closer to fortune-telling.
Primarily, yes. It was about omens. The sky was where the gods lived, and their movements were messages. If Mars rises in the house of the crab, the king will have a bad harvest. That sort of thing. They were looking for correlations, for patterns between the heavens and events on Earth.
The big shift to asking why things move, to asking about the physical machine of it all, that really begins with the Greeks.
Yes. The Greeks inherited the Babylonian data, but they brought a new question to the table. What is the underlying reality?
Right. And the Greeks, they had some brilliant ideas, obviously, but they were also kind of stuck on aesthetics, on beauty.
You can basically blame Plato for that. Plato argued that the heavens were the realm of the divine, the realm of perfection, and what is the most perfect, most symmetrical shape?
A sphere.
The sphere. And what is the most perfect motion?
A circle.
Uniform circular motion. So the Greeks decided, as a matter of philosophical principle, before they even really looked at the data, that the universe must be made of spheres and all motion must be perfect circles.
Which turned out to be a massive headache for everyone for the next 2,000 years.
A huge headache. A 2-millennium-long detour, you could say, because nature doesn't care about your philosophical preferences. You had brilliant minds like Eudoxus trying to explain the observed motion of the planets by stacking invisible crystalline spheres inside each other, like Russian nesting dolls, all spinning at different speeds and on different axes.
It sounds incredibly complicated.
It was. But at the center of it all was one unshakable assumption.
The Earth.
Of course, the geocentric model. It just makes intuitive sense, doesn't it? You stand outside, you don't feel the Earth moving, you see the sun rise in the east and set in the west. It certainly looks like everything is spinning around us.
But there were problems. The planets were the real troublemakers. The word planet comes from the Greek for wanderer, right?
That's right, planets. Because the stars, the fixed stars, they stay in their patterns. Orion always looks like Orion, but The planets, Mars, Jupiter, Saturn, they drift through the constellations, and sometimes they do something really, really weird.
They go backward.
They stop, they turn around, they go backward for a few weeks, what we call retrograde motion, and then they turn around again and continue on their way.
Now, if you have a sun-centered, a heliocentric model, this is super easy to explain.
Trivial, yeah. Imagine you are in a race car on the inside track of a speedway, and you're about to overtake a slower truck on the outside track. As you pass it, from your perspective, the truck seems to be moving backward against the background scenery of the stands.
That's just Earth lapping Mars in our orbit.
Precisely. But if you are stuck with the Earth in the center, and you are chained to this dogma of perfect circles, how on earth do you explain a planet doing a loop-de-loop in the sky?
You invent an insane contraption.
You get Claudius Ptolemy. In the 2nd century CE, he wrote the book that would define astronomy for the next 1,500 years, the Almagest, which means the greatest, and he built this absolute Rube Goldberg machine of a universe to save the geocentric model.
Okay, so break it down. What was his solution?
He said, okay, the planet doesn't move on the big circle around the Earth. Instead, the planet moves in a small circle called an epicycle.
A little wheel.
A little wheel. And the center of that little wheel moves along the big circle around the Earth, which he called a deferent.
So it's wheels within wheels, like drawing with a spirograph.
That is the perfect analogy. Or it's like the teacups ride at Disneyland. You are spinning in your own little cup while the whole platform you're on is also spinning. If you traced your path from above, you'd get these loops.
And it was even more complicated than that, wasn't it?
Oh, yeah. He had to add equants and eccentrics. He had to offset the Earth from the true center. It was incredibly complex math. But, and this is the crucial point, this is why it lasted for 1,500 years. It worked. His model could predict where Mars would be next Tuesday with pretty good accuracy.
So the model was completely wrong physically, but the math was useful for prediction.
Which is a great lesson in the history of science. A model's predictive power doesn't necessarily mean it reflects reality.
Now, in the standard telling of this story, we usually jump from the Greeks straight to Copernicus and the Renaissance. But the source makes a really important point to highlight what was happening while Europe was in the so-called Dark Ages.
The intellectual center of gravity shifted east,
The Baghdad.
the House of Wisdom. From about the 8th to the 13th century, while Europe was largely losing direct access to the Greek texts, Arabic and Persian astronomers were translating Ptolemy, preserving that knowledge, refining his measurements, building better instruments like astrolabes, and critiquing his work.
And that's why so many of the proper names for stars today are Arabic, isn't it?
It is. Rigel, Aldebaran, Altair, Deneb, even Betelgeuse, our dying giant, comes from the Arabic Yad al-Jalza, meaning the hand of the giant. That's a direct legacy of this golden age of Islamic astronomy. They were the bridge that carried classical knowledge into the Renaissance.
And then even further east, you have the Chinese. And their whole approach was different, wasn't it? The Greeks were obsessed with the idea that the sky was perfect and unchanging, but the Chinese seemed to embrace the chaos.
They did. The Chinese imperial astronomers were essentially the emperor's celestial watchmen. Their job was to look for anything new, anything that disrupted the established pattern. They called them guest stars.
So comets, novae, supernovae.
Anything that wasn't supposed to be there. And because they weren't blinded by this Greek philosophical dogma that the heavens are immutable, they actually recorded spectacular events that the Europeans completely ignored.
The big famous example here is from the year 1054 CE.
Yes, the year of the Great Supernova. A star in the constellation Taurus exploded. It was so bright you could apparently read by its light at night. For about 3 weeks, you could see it during the daytime. Chinese astronomers recorded it in great detail, its position, its brightness over time. We even have records from Japanese and Arabic astronomers.
And what was happening in Europe at that time?
Crickets. Silence. There is almost no record of this spectacular event in any European chronicles from the time. It's possible they just weren't looking up, but it's more likely that the monks and scholars who kept the records were so wedded to the Aristotelian idea that the sky cannot change that they literally filtered it out of their reality. They saw it, but they couldn't process it.
It didn't fit the model, so the data must be wrong.
Exactly. It's a powerful example of cognitive bias shaping scientific observation. We can still see the remnant of that explosion today, by the way. It's called the Crab Nebula.
That is incredible. But eventually that bias has to break. That brings us to section 2 of our story, the revolution, moving the center of the universe.
And that story starts with one name, Copernicus, 1543.
the man who stopped the sun and moved the earth. But the source is this great line. It calls his book De Revolutionibus, the book nobody read.
And that's largely true. It was incredibly dense, filled with technical Latin and complex geometry. Copernicus wasn't some kind of firebrand revolutionary. He was a canon in the Polish church. He was a cautious man. He actually waited until he was on his deathbed to allow it to be published because he knew it would cause trouble.
So what was his big idea? What was his argument?
His argument was fundamentally about elegance. He looked at Ptolemy's system with all its epicycles and equants and said, "This is a mess. This is not how God would have designed the universe." His argument was basically, look, guys, if we just do one thing, if we put the sun in the center, we don't need all these epicycles to explain retrograde motion. The loop-de-loop of Mars just happens naturally as fast Earth overtakes it.
Occam's razor. The simplest explanation is usually the best one.
That was his core belief. But here's the catch. It wasn't perfect. Copernicus was still a man of his time, and he still believed in Plato's perfect circles. He couldn't let them go. So his model, while philosophically cleaner, actually didn't work much better than Ptolemy's when it came to predicting where the planets would be.
So it was a beautiful idea that didn't quite match the facts yet.
Not yet.
Okay.
To really fix the model, we needed better data, much better data.
Enter Tycho Brahe. Now, we have to talk about Tycho. He is not your typical stuffy academic scientist.
Not even close. Tycho was a Danish nobleman, just a larger-than-life character in every respect. He famously lost the bridge of his nose in a duel with his cousin over who was the better mathematician.
You're kidding.
Not at all. It was at a wedding party. So for the rest of his life, he wore a prosthetic nose made of a gold and silver alloy that he would apparently glue on. He also had a pet moose that he would bring to parties, which unfortunately met its end when it got drunk on beer at a dinner and fell down a flight of stairs.
You cannot make this stuff up. This is a real historical figure.
Absolutely. But despite all these eccentricities, he was the greatest observational astronomer of the pre-telescope era. The King of Denmark gave him an entire island, the Island of Men, and a huge budget, and he built this castle observatory called Uraniborg, the Castle of the Heavens.
And what did he do there?
He built instruments on a scale never seen before, massive wall quadrants, huge sextance instruments the size of a building, all designed to measure the positions of the stars and planets with insane, unprecedented precision. He did this night after night for decades.
Just collecting data.
Yes, he created this catalog of planetary and stellar positions that was 10 times more accurate than anything that had come before it. But Tycho himself had a weird model of the universe. He saw the mathematical elegance of Copernicus, but he just couldn't bring himself to accept a moving Earth. He argued that a heavy, sluggish Earth couldn't possibly be flying through space.
So what was his compromise?
He proposed a hybrid model, a halfway house. In Tycho's universe, the planets orbit the sun, but the sun and moon orbit the Earth.
So he kept the Earth in the center to satisfy his intuition.
Right. But his greatest contribution wasn't his model, it was his data. And the fact that he hired a brilliant and very strange young assistant named Johannes Kepler.
The complete opposite personality to Tycho.
Totally. Kepler was a devout, mystical, brooding German mathematician. He came from a poor family, had a very difficult life. He was hired by Tycho to crunch the numbers and prove Tycho's own hybrid model was correct.
And then Tycho died, rather famously.
Yes, the story goes his bladder burst because he was too polite to excuse himself from a royal banquet. That's probably an exaggeration, but he did die of a bladder infection. And Kepler, through some very shrewd maneuvering, managed to get his hands on Tycho's gold mine, all those precious data logs.
And this began what Kepler himself called his war on Mars.
Yes. He spent the next several years battling that data. He tried to fit Tycho's incredibly precise observations of Mars into a circular orbit, and he almost did it. He got it to match the data to within 8 minutes of arc, which is a tiny, tiny sliver of the sky, about the width of a pencil lead held at arm's length.
Most people would have just rounded up and said, good enough.
Exactly. Ptolemy would have said good enough. Copernicus would have said good enough. But Kepler had an almost religious faith in the quality of Tycho's data. He knew Tycho's eyes and his instruments were better than that. He famously wrote, "If I had believed that this 8-minute error was negligible, I would have patched up my hypothesis. But since it was not permissible to ignore, these 8 minutes pointed the path to a complete reformation of astronomy."
So he knew the error was in the theory, not the data.
He did. So in a stroke of absolute genius and real intellectual courage, he threw out 2,000 years of tradition. He abandoned the perfect circle. He tried other shapes. And finally, he tried an ellipse, an oval, A squashed circle.
Awesome.
It fit perfectly, like a key sliding into a lock.
That moment, you could argue that is the birth of modern astrophysics.
Yeah.
Breaking the spell of the perfect circle.
It changed everything. It was the first of his 3 laws of planetary motion. The first law, orbits are elliptical. The second, planets don't move at a constant speed. They sweep out equal areas in equal times, meaning they speed up when they are close to the sun and slow down when they're far away. It wasn't a divine clockwork of crystal spheres anymore. It was a physical system governed by forces.
But we still needed to see it. We needed the hardware to prove it to the skeptics. Which brings us to 1609 and to Galileo.
The telescope. Now, it's a common misconception that Galileo invented it. He didn't. A Dutch spectacle maker named Hans Lippershey filed the first patent in 1608. But Galileo heard a description of this new spyglass, and without ever having seen one, he figured out how it worked and built his own.
And he made it better.
Much better. He ground his own lenses, and he quickly improved it from 3x magnification up to 20x, then 30x. He had the best telescope in the world. And then he did the revolutionary thing. He pointed it up at the sky.
And in doing so, he basically destroyed the old universe in the space of about 2 weeks.
It was an avalanche of discovery. Every time he looked at something new, he shattered another piece of the old Ptolemaic Aristotelian system.
So let's go through them. What were the key things he saw that just completely broke the old model?
Okay, first, the moon. Aristotle and the Church taught that celestial bodies are perfect, smooth, unblemished spheres. Galileo pointed his telescope at the moon and saw mountains, craters, valleys. He even measured the height of the mountains by the length of their shadows. The moon wasn't some perfect celestial orb. It was a world just like Earth, rough and dirty and imperfect.
So that's strike one against celestial perfection.
Big strike one. Then he turned to Jupiter. He saw what he thought were 3 little stars lined up next to it. The next night he looked again, and they had moved. But they were still with Jupiter. Night after night he tracked them. He saw a 4th one. He realized they were moons orbiting Jupiter.
The Galilean satellites.
Yes, and this was a profound discovery because it proved that not everything revolves around the Earth. There could be other centers of motion in the universe. It was a miniature solar system.
Strike two. That's a huge blow to the geocentric model.
A killer blow. But the final nail in the coffin was Venus. According to Ptolemy's model, Venus should only ever show a crescent or new phase from our perspective. But Galileo watched Venus over many months, and he saw that it goes through a full set of phases, just like our moon. It goes from a thin crescent to a half phase to a gibbous phase to nearly full.
And that's only possible if...
It's geometrically impossible if Venus and the Sun are both orbiting the Earth. It only works if Venus is circling the Sun.
Strike three. The geocentric model is officially dead.
It was. The evidence was irrefutable. You could look through the tube and see the truth with your own eyes. The Church fought back, of course, famously putting Galileo under house arrest for the rest of his life for heresy. But the genie was out of the bottle.
So by the mid-1600s, we have a new picture. We know the Earth moves, we know the planets orbit the Sun, and thanks to Kepler, we know they move in ellipses. But we don't know why. Why don't the planets just fly off into space in a straight line? What's holding them? Why do they speed up and slow down?
This is the final piece of the classical puzzle, the grand synthesis. And it comes from Isaac Newton.
The Apple story. Is there any truth to that?
He used the anecdote himself later in life, so it's probably based in truth, even if it's been romanticized. The setting is his family home in Woolsthorpe, where he had gone to escape the plague in London in 1666. He was sitting in an orchard, he watched an apple fall from a tree, and he looked up at the moon, visible in the daytime sky, and he asked the critical, brilliant question, does the force that pulled that apple down, does that same force reach all the way to the moon?
And the answer was yes.
The answer was yes. He called it universal gravitation. He realized that gravity isn't some special force unique to Earth, it's universal. Every object with mass pulls on every other object with mass. He also realized that this force gets weaker with distance. Specifically, it follows an inverse square law. Double the distance, and the force is only 1/4 as strong.
So the moon is effectively falling toward the Earth, just like the apple.
Exactly. But it also has a huge amount of sideways speed from its formation. So as it falls, the Earth curves away beneath it. It keeps falling and keeps missing. That is what an orbit is.
A constant myth.
A free fall that never ends. And the beauty of it was that Newton's new mathematics calculus, which he invented for this purpose, could derive all of Kepler's laws from this one simple principle of gravity. The ellipses, the speeding up and slowing down, it all just fell out of the math.
He wrote the rule book for the cosmos?
Yeah.
And the first big proof of his system came from a comet, didn't it?
Yes, from his friend Edmund Halley. Halley was fascinated by comets, which until then were seen as unpredictable, one-off omens. He used Newton's new math to calculate the orbits of dozens of them from historical records, and he noticed something striking. He saw that the comets recorded in 1531, 1607, and 1682 all had almost the exact same elliptical orbit.
So he realized it wasn't three different comets.
He made a bold prediction. He said, "This is the same object returning every 76 years, and it will be seen again in 1758.
Halley himself died before 1758.
He did. He never got to see if he was right. But on Christmas night, 1758, a German farmer and amateur astronomer spotted it. It returned exactly as predicted. It was the first time humanity had predicted the return of a celestial visitor. It was the ultimate triumph of Newtonian physics. It was the moment astronomy graduated from just observation to a predictive physical science. We had the code.
So we have the map, we have the physics of motion, we know where things are and how they move. But looking at a dot of light in the sky doesn't tell you what it is. Is it a rock? A distant fire? A hole in the curtain of heaven? This brings us to section 3, the rise of astrophysics. Finally, we get to decode the light itself.
This is the second great revolution in astronomy. The first was about where. The second revolution is about what. And the key that unlocked it all is a technique called spectroscopy.
Okay, so let's break this down for a second. Newton, back in the 1600s, he split sunlight with a prism and got a rainbow, a spectrum. But it took another 150 years for scientists to look closer and see something was missing from that rainbow.
That's right. In the early 1800s, scientists like Wollaston and Fraunhofer looked at the solar spectrum through much better equipment. And they saw you don't just get a smooth, continuous rainbow. You see hundreds of thin, dark, black lines cutting through the colors. Fraunhofer mapped over 500 of them, but nobody knew what they were. They were just a curiosity.
Like a barcode printed over the rainbow.
That's the perfect analogy. A cosmic barcode. The mystery was solved in the 1850s by Bunsen and Kirchhoff. They were burning different chemicals in a flame and looking at the light through a prism. And they found that each chemical, when heated, emits light at only a few very specific colors, a few bright lines.
So a bright line spectrum.
Yes. And then it came the breakthrough. They realized that if you shine a continuous rainbow of light through a cool gas of that same chemical, the gas absorbed the exact same colors it would otherwise emit, so you get a continuous spectrum with dark lines, an absorption spectrum.
And those dark lines matched the dark lines from the sun.
They matched perfectly. The dark lines in the sun's spectrum were the atomic fingerprints of chemical elements in the sun's atmosphere, absorbing certain colors of light coming from the hotter surface below.
This is mind-blowing if you stop and think about it. It means we can look at a star 1 trillion miles away, split its light, run it through a spectroscope, and say, with certainty, that star has iron in its atmosphere, or sodium or calcium.
It was a monumental leap. It allowed us to do chemistry across the cosmos from a lab on Earth. We finally realized the stars are made of the same stuff we are. Mostly hydrogen and helium, as it turned out, with sprinklings of all the other elements. The universe was no longer just a collection of moving points. It was a physical place with a chemical composition we could study.
But there were millions of stars, and they all had different barcodes, different spectra. It must have been an absolute chaos of data. Someone had to sort this mess out.
This brings us to the Harvard College Observatory in the 1890s. The director at the time, a man named Edward Pickering, had a problem. He was pioneering the use of photography to capture the spectra of thousands of stars on glass plates. He had piles and piles of this raw data, and he needed it analyzed and classified.
And his male assistants weren't up to the task, as the story goes.
The story is he was frustrated with them and famously said his maid could do a better job. So he hired his maid, Williamina Fleming, and she did a brilliant job. He then went on to hire a whole team of women to do this meticulous classification work. They were known, rather unfortunately, as Pickering's harem, or more respectfully, the Harvard computers.
And they were literally doing the work that digital computers do for us now, processing massive amounts of data.
Manually. They were looking at these tiny smudges on fragile glass plates with magnifying glasses hour after hour, day after day. It was tedious, eye-straining, low-paid work. But among them was a woman named Annie Jump Cannon, who was an absolute virtuoso. She could apparently look at a stellar spectrum and classify it in a matter of seconds.
She had a gift for pattern recognition.
An incredible gift. Over her career, she personally classified the spectra of over 350,000 stars. And in doing so, she threw out the old, clunky classification system and created the one we still use today.
The OBAFGKM system.
That's the one. It's a temperature sequence. O stars are the hottest, bluest, and most massive. M stars are the coolest, reddest, and smallest. Our sun is a G-type star, a nice, average yellow dwarf right in the middle.
And there's a famous mnemonic for that, isn't there? Generations of astronomy students have used it.
Oh, be a fine girl or guy, kiss me. It's a classic. Cannon's work was foundational. It turned a chaotic zoo of stars into an ordered system.
And once Cannon organized all that data, another, even deeper pattern emerged. The Hertzsprung-Russell diagram.
The HR diagram. You could argue this is the single most important graph in all of astronomy. It was developed independently by Ejnar Hertzsprung in Denmark and Henry Norris Russell in the US. The idea is simple. You make a graph. On the horizontal axis, you plot a star's temperature or a spectral type O, B, A, F, G. And on the vertical axis, you plot its true brightness, its luminosity.
And when you plot all the stars on this graph, they don't just land randomly everywhere.
Not at all. They cluster in very specific regions. Most of them, about 90%, fall in a neat diagonal line that runs from the hot, bright stars in the top left corner down to the cool, dim stars in the bottom right.
The main sequence.
The main sequence. And then you have some outliers. You have a clump of very bright but cool stars up in the top right, the red giants and supergiants. And you have a little group of very hot but very dim stars down in the bottom left, the white dwarfs.
So what did that tell us? Why is that so important?
It told us that stars aren't static objects. They have a life cycle. They evolve. The HR diagram is like a snapshot of a town's population. You see lots of adults, the main sequence, some children, and some elderly people. It revealed that stars are born, they settle onto the main sequence for the long, stable adult phase of their lives where they burn hydrogen into helium in their cores. And then when they start to run out of fuel, they move off the main sequence to become giants, and eventually they die and become white dwarfs. It gave stars a biography.
So by the early 1900s, we understand what stars are made of, and we understand their life cycle. But we still have a major misconception about the sheer scale of the universe. We thought the Milky Way was it. The whole show.
That was the prevailing consensus, the island universe theory, as it was called. We thought the Milky Way was this vast, lonely island of stars in an infinite empty ocean of nothingness. And those fuzzy little spiral smudges we could see in our telescopes. We thought they were just small clouds of gas inside our own galaxy, maybe solar systems in the process of forming.
This led to what's known as Great Debate in 1920.
A very famous public debate between two heavyweight astronomers of the day, Harlow Shapley and Heber Curtis. Shapley argued that the Milky Way was huge, much larger than previously thought, and that it was the entire universe. Curtis argued that the Milky Way was smaller and that those spiral nebulae were, in fact, other galaxies, other island universes, just like our own, but at immense distances.
And the man who finally settled it was a former lawyer named Edwin Hubble.
Yes, Edwin Hubble, a fascinating character. He was a lawyer, a boxer, a high school basketball coach. And then he decided to become an astronomer. He went to work at the Mount Wilson Observatory in California using the new 100-inch Hooker telescope, the biggest and most powerful telescope in the world at the time.
And he pointed it at one of those spiral smudges.
At the biggest and brightest one, the Andromeda Nebula. He spent night after night taking long exposure photographs of its outer regions, and he was looking for a very specific type of star called a Cepheid variable.
We need to explain this yardstick. This is a crucial piece of the puzzle. What is a Cepheid?
A Cepheid is a type of giant star that is unstable. It physically pulses, it gets bigger and smaller, and as it does, its brightness changes in a very regular, predictable rhythm. It gets brighter and dimmer like a lighthouse beacon.
And the key discovery was made by another one of the Harvard computers.
Yes, by Henrietta Leavitt. She was studying Cepheids in a nearby galaxy called the Small Magellanic Cloud. And she discovered something brilliant. She found a direct mathematical relationship between the period of the pulse, how long it takes to go from bright to dim and back again, and the star's true intrinsic brightness.
So if you can time the pulse, you know how bright the light bulb should be.
Exactly. The faster it pulses, the dimmer its true luminosity. The slower it pulses, the brighter it is. And if you know how bright a light bulb really is and you can measure how dim it looks to you from a distance, you can calculate exactly how far away it is. It's what astronomers call a standard candle.
A standard candle to measure the universe.
Yeah.
So Hubble found one of these blinking stars in the Andromeda Nebula. He timed its pulse, he did the math.
And he realized that for the star to be that dim, it had to be impossibly far away. His initial calculation was about 1 million light years. We now know it's closer to 2.5 million. But either way, it was an immense distance, way, way, way outside the boundaries of our own Milky Way galaxy.
That moment, It's not just a discovery, it's a complete rescaling of reality. It's like living your whole life on one small island and then realizing there are billions of other continents.
It's bigger than that. In one night, the known universe went from being a single galaxy a few 100,000 light years across to being a cosmos of billions of galaxies stretching for millions, maybe billions of light years. The scale of reality just exploded.
But Hubble wasn't done shaking things up. He started studying these other galaxies, and he noticed something else about their light.
Yes, he started taking spectra of them, and he found that their light, the barcode of their elements, was almost always redshifted.
Which is the Doppler effect for light.
Just like the siren of an ambulance drops in pitch as it drives away from you, the wavelength of light from an object moving away from you gets stretched out. It shifts toward the red end of the spectrum. Hubble saw that almost every galaxy he looked at was redshifted. They were all running away from us.
And not just running away, there was a pattern. The farther away a galaxy was, the faster it was running away.
Hubble's law, a simple linear relationship. This was the first piece of evidence that the universe as a whole is expanding. It's not just that galaxies are flying through a static space. Space itself is stretching, carrying the galaxies along with it.
Which leads to a truly inevitable and mind-bending question. If everything is getting bigger and further apart, that means yesterday it was all a little smaller and closer together, and a billion years ago it was smaller still.
Run the film backward.
Yeah.
If you rewind the cosmic expansion, eventually everything, all the matter, all the energy, space, and time itself is crushed into a single point of unimaginable density and temperature.
The Big Bang.
A term that was actually coined as an insult. It came from the British astronomer Fred Hoyle on a BBC radio show in 1949. He meant it as a term of mockery. He thought the idea of a beginning to the universe was unscientific and absurd. He was a champion of the steady-state theory, the idea that the universe has always existed and always will.
But the universe had a surprise in store to prove him wrong. And the evidence was found, of all places, in annoying background noise.
The cosmic microwave background, the CMB. In 1964, two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were calibrating a new, very sensitive horn antenna. And they kept getting this persistent, annoying, low-level hiss. It was coming from every direction in the sky, day and night. They thought it might be pigeon droppings on the antenna causing interference. They literally climbed up and cleaned it out.
And the hiss was still there.
It was still there. And it wasn't pigeons. It was the afterglow of creation. It was the leftover heat from the Big Bang itself, the light from the primordial fireball, cooled down by 13.8 billion years of cosmic expansion to just 2.7 degrees above absolute zero. It was the smoking gun for the Big Bang theory.
So we have a beginning, but do we have an end? The source mentions a final modern twist in this story: dark energy.
This is the plot twist of the last few decades. For most of the 20th century, we assumed that the gravity of all the galaxies would eventually put the brakes on the expansion. The big question was, is there enough gravity to slow it down, stop it, and maybe even reverse it into a big crunch?
But that's not what we found.
Not at all. In the late 1990s, two independent teams of astronomers were using distant supernovae as standard candles to measure the expansion rate of the universe very precisely. And they found the opposite of what they expected. The expansion isn't slowing down, it's accelerating.
Because speeding up, how is that possible?
We don't know. There's some mysterious energy, some property of space itself that is pushing everything apart, fighting against gravity. We call it dark energy because we have absolutely no idea what it is. And it's winning. It makes up about 70% of the total energy budget of the universe.
It is slightly terrifying.
Yeah.
It suggests a very lonely, cold future.
It does. It points towards a big freeze or big rip. If it continues, galaxies will eventually be pushed so far apart from each other that their light will never be able to reach us. The night sky will go dark, one galaxy at a time.
On that cheerful note, let's pivot. Section 5. We've spent thousands of years looking up at the sky. In the 20th century, we finally decided to go there, the space age.
This is where astronomy meets engineering and geopolitics. And it really starts not with scientists, but with dreamers. Jules Verne writing about shooting people to the moon in a giant cannon, which would have turned them into jelly, by the way, but he inspired the real pioneers.
Like Tsiolkovsky in Russia and Robert Goddard in America.
Exactly. Tsiolkovsky worked out the theoretical rocket equation, the physics of it. Goddard was the practical experimenter, building and launching the first liquid-fueled rockets in secret in the New Mexico desert.
And he was mocked for it, right? The New York Times wrote a famous editorial saying he didn't understand high school physics because rockets won't work in a vacuum.
Because they mistakenly thought a rocket needed air to push against. They were completely wrong. A rocket works by throwing mass out the back at high speed to push the ship forward. It's pure Newton's third law. For every action, there's an equal and opposite reaction. But it took a world war to turn these small experiments into a mature technology.
The V-2 rocket.
Wernher von Braun and his team in Nazi Germany, they developed the V-2 ballistic missile to bomb London. It was a weapon of terror. But technologically, it was the first man-made object to cross the Kármán line, the edge of space. After the war, both the U.S. and the Soviets scrambled to capture the German scientists and the V-2 hardware.
And the Cold War turned space from a scientific curiosity into a geopolitical battleground.
Sputnik, October 4th, 1957, a shiny metal ball the size of a beach ball circling the Earth, beeping. It terrified the West. It was a profound psychological shock. It meant the Soviets had the high ground and could, in theory, drop a bomb from orbit.
And they kept racking up the first.
They did. They sent Laika the dog into orbit. Then in 1961, Yuri Gagarin became the first human being in space. He completed one orbit of the Earth.
The ultimate propaganda victory for the Soviets.
It was. The U.S. was humiliated. They were blowing up rockets on the launch pad on national television. That is the context for Kennedy's famous moon speech. Quote, "We choose to go to the moon in this decade, not because it is easy, but because it is hard." It wasn't really about science. It was about beating the Soviets.
The Apollo program. It's hard to overstate the sheer scale of this undertaking.
400,000 people worked on it. The Apollo guidance computer on board had less processing power than a modern singing birthday card. They were inventing the technology as they went. They were flying by the seat of their pants with slide rules and raw courage.
The source highlights Apollo 8. We always focus on Apollo 11's landing, but 8 was a critical and audacious step.
Apollo 8 was Christmas 1968. Frank Borman, Jim Lovell, Bill Ambers. They were the first humans to ever leave Earth gravity well, the first to travel to another world and orbit it. And while in lunar orbit, they took that photo Earthrise, the beautiful, fragile blue marble of Earth rising over the dead, gray lunar surface.
It's been credited with helping to launch the modern environmental movement.
It absolutely did. As the astronaut Bill Anders said, "We came all this way to explore the moon, and the most important thing is that we discovered the Earth."
And then, of course, July 20th, 1969, Apollo 11. Armstrong and Aldrin in the Mare Tranquillitatis.
The Sea of Tranquility. And that landing was incredibly hairy. The guidance computer was sounding alarms. They were running critically low on fuel. Armstrong had to take manual control and fly the lander over a field of boulders to find a safe spot. His heart rate was over 150, but they touched down. The Eagle has landed.
And they brought back rocks, but they also brought back descriptions. The smell of the moon dust.
Yes. When they got back inside and took their helmets off, they said the lunar dust that had gotten on their suits smelled like spent gunpowder. It's very fine, very abrasive stuff.
The program ended just a few years later with Apollo 17 and Harrison Schmitt.
The only professional scientist, a geologist, to walk on the moon. He found orange soil, evidence of ancient volcanic activity. But since 1972, no human has gone beyond low Earth orbit. We've been stuck close to home.
We built space stations instead. Skylab, the Russian Mir, and now the International Space Station.
We learned how to live and work in space for long periods, how to do science in zero-G, how to stop our bones from dissolving and our eyeballs from changing shape. And we built the space shuttle to service those stations.
A beautiful but incredibly complex and flawed machine.
It was a space truck. It did amazing things. It deployed the Hubble telescope. It built the ISS piece by piece. But it was fragile and unforgiving. The tragedies of Challenger and Columbia were brutal reminders that space is never ever routine. It is always trying to kill you.
And now we've entered a new commercial era, haven't we? With companies like SpaceX.
Landing rockets. That is the new revolution. Seeing a Falcon 9 first stage come back and land itself upright on a drone ship, it's just science fiction made real. And if you can reuse the most expensive part of the rocket, the cost of getting to orbit drops by 90% or more. That is what opens the door to truly settling space, to going back to the moon and on to Mars.
Speaking of Mars, let's talk about the robots. Section 6. While humans have stayed close to home, our robotic envoys have gone on the grand tour of the solar system.
This is my absolute favorite era of space exploration, the Voyager missions in particular.
Voyager 1 and 2. Launched in the summer of 1977. Why then specifically?
Because of a very rare planetary alignment. Once every 176 years, the outer planets, Jupiter, Saturn, Uranus, and Neptune, align in a specific curve. This allowed a spacecraft launched at just the right time to use a technique called a gravitational slingshot.
Okay, so explain that. How do you sling around a planet? You're not using a rope.
No. Imagine the planet is a speeding train. You're a kid on a skateboard. As the train goes past, you grab the handle on the side of the last car. The train whips you around and throws you forward with extra speed. In the process, you steal a tiny, tiny fraction of the train's momentum. That's what Voyager did. It used Jupiter's gravity to fling it towards Saturn, then Saturn's to fling it to Uranus, and so on.
So Voyager essentially bounced from planet to planet.
Exactly. It turned a trip that would have taken 40 years into a 12-year trip, and the discoveries were just breathtaking. We saw Jupiter's Great Red Spot was a raging hurricane bigger than 3 Earths. We discovered active volcanoes on its moon Io and a hidden ocean under the ice of Europa. We saw Saturn's rings were not solid, but made of thousands of tiny, intricate, groove-like ringlets.
And Voyager 2 went on to the ice giants, Uranus and Neptune.
It's still the only spacecraft to have ever visited them. It was a journey into the true deep dark. It saw the Great Dark Spot on Neptune, a storm with winds blowing at over 1,000 miles per hour. Just an incredible accomplishment.
And on board both of these ships is the famous Golden Record.
A message in a bottle thrown into the cosmic ocean. It's a phonograph record made of gold-plated copper, designed to last for 1 billion years. It's encoded with sounds of earth whales, thunder, a baby crying, a kiss. It has music from around the world back, Chuck Berry tribal chants, and it has greetings in 55 human languages. It's a message to whatever alien civilization might stumble upon it in the distant future.
It's like saying, this is who we were. This is what our world sounded like.
It's incredibly poignant. Voyager 1 is now the most distant human-made object out in interstellar space. It's our silent ambassador to the stars.
Let's zoom back in from the solar system to the stars themselves. Section 7. The physics of stars. We know they are hot, we know they are made of hydrogen, but for a long time we didn't know why they shine.
This is the big energy crisis of the 19th century. Physicists like Lord Kelvin calculated that if the sun was just a giant ball of burning coal, it would burn out in a few thousand years. If it was shining by slowly collapsing under its own gravity, it could only last for a few million years. But geologists were finding rocks and fossils that were clearly hundreds of millions, even billions of years old.
So the sun couldn't possibly be younger than the Earth it was shining on.
Right. It was a major paradox. There had to be a missing energy source, something incredibly powerful. Einstein provided the key in 1905 with his famous equation, a He-2n-2. Mass is just a super concentrated form of energy. If you could find a way to convert even a tiny amount of mass into pure energy, you would get an immense power output.
Nuclear fusion.
Exactly. Scientists like Arthur Eddington and Hans Bethe figured out the process in the 1920s and 30s. In the core of the sun, the temperature and pressure are so extreme, 15 million degrees Celsius, that hydrogen atoms are smashed together with enough force to overcome their natural repulsion. They fuse to form helium. But here's the trick. One helium atom weighs slightly less than the 4 hydrogen atoms that went in to make it.
So where does that missing mass go?
It's converted directly into energy. Gamma rays, heat, light, that tiny mass defect, as it's called, is what has powered our sun for 4.6 billion years, and it's what powers every star in the universe.
And we proved this was happening with the strange neutrino detectors deep underground.
We did. The fusion process produces these bizarre particles called neutrinos, ghost particles, that have almost no mass and hardly interact with anything. They stream right out of the sun's core and fly through the Earth as if it weren't there. To catch them, we had to build giant tanks of cleaning fluid or ultra-pure water deep in mines to block out all other radiation and just wait for one neutrino in a trillion to happen to hit an atom. And we did it. We caught them. It was direct proof that the sun is a gigantic fusion reactor.
But the hydrogen fuel doesn't last forever. And then we get to the stellar graveyards. This is where the physics gets really extreme, really sci-fi.
It all depends on the star's mass. A star like our sun, at the end of its life, will gently puff off its outer layers to create a beautiful planetary nebula. And it will leave behind its dead core, a white dwarf. This is a collapsed object made of carbon and oxygen about the size of the Earth, but containing the mass of the sun.
So it's incredibly dense.
Unimaginably dense. A single teaspoon of white dwarf material would weigh as much as an elephant on Earth. The only thing holding it up against gravity's crush is something called electron degeneracy pressure. Basically, the electrons are squeezed together so tightly that a quantum mechanical law kicks in that says they can't be in the same place at the same time, so they push back.
But if the star is more massive than the sun,
then gravity can overwhelm even that electron pressure. There's a weight limit for a white dwarf, called the Chandrasekhar limit. Cross that, and the star collapses further, catastrophically. The collapse is so violent that electrons are smashed into protons, turning them into neutrons. You get a neutron star.
And how dense is that?
Now you're taking the mass of 1.5 suns and squeezing it into a ball the size of Manhattan. A single teaspoon would weigh 1 billion tons. The gravity is so intense that if you dropped a marshmallow on a neutron star, it would hit the surface with the energy of a nuclear bomb.
And if that neutron star is spinning?
It becomes a pulsar. As it collapses, its rotation speeds up like an ice skater pulling in their arms. It can spin hundreds of times a second, and it has a powerful magnetic field that shoots out beams of radiation from its poles. As it spins, those beams sweep across the sky like a lighthouse. And if one of those beams happens to sweep across the Earth, our radio telescopes detect it as a very rapid, very precise pulse. Beep, 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 beep.
And the final stage. For the real heavyweights of the universe.
Black holes. If the collapsing core is more than about 3 times the mass of our sun, nothing can stop the collapse. Not even the neutrons can hold up. The star collapses forever, down to an infinitely small, infinitely dense point. A singularity.
And the gravity in its vicinity is so strong that nothing, not even light, can escape once it crosses a certain boundary.
The event horizon. The point of no return. Hence black. But Stephen Hawking added a fascinating quantum twist to this. He showed that due to quantum effects right at the edge of the event horizon, black holes aren't truly black. They should emit a very faint, very cold thermal glow. Hawking radiation.
So they can evaporate.
In theory, yes. But the process is so incredibly slow that for a solar mass black hole, it would take longer than the current age of the universe, trillions upon trillions of times over. They will be the last things left in the universe long after the last star has died.
To see all this, from distant galaxies to black holes, we've had to constantly upgrade our eyes. Section 8. The modern toolkit. It's not just about bigger lenses anymore, is it?
No, we hit a wall with traditional telescopes in the 20th century. The problem is the Earth's atmosphere. It's like trying to look at the world from the bottom of a swimming pool. The turbulence in the air blurs and distorts the light. It's what makes stars twinkle, which is romantic, but it's terrible for getting sharp data.
So we invented adaptive optics.
This is just incredibly cool technology. We shoot a powerful laser up into the sky to create a small, bright spot, a fake star. Computers on the ground monitor how the atmosphere makes that fake star twinkle. Then, they send commands to tiny pistons on the back of the telescope's main mirror, causing it to bend and flex hundreds of times a second to perfectly cancel out the atmospheric distortion in real time.
It's like noise-canceling headphones, but for light.
That is the perfect analogy. It allows a telescope on the ground to take pictures that are almost as sharp as a telescope in space.
But we also just went to space. The Hubble Space Telescope.
The legend. Launched in 1990, it had a famously blurry mirror at first, a tiny manufacturing error the width of a human hair. But astronauts on a shuttle mission went up and installed corrective optics, like giving it a pair of glasses. And since then, my God, the images it's produced have become cultural icons, the pillars of creation, the deep field.
Tell us about the deep field.
That was a gamble. They pointed Hubble at a tiny, completely blank patch of sky near the Big Dipper, a spot that looked utterly empty, and they just let the camera shutter stay open for over 100 hours, collecting every single photon. And when they processed the image, it wasn't empty. It was filled with 3,000 galaxies.
Every smudge a galaxy.
Some of them so distant we're seeing them as they were over 12 billion years ago. It was a core sample of the universe.
And now we have its successor, the James Webb Space Telescope.
Webb is a different beast. It's much larger than Hubble, and it's designed to see in the infrared part of the spectrum. This allows it to do 2 things. It can see through the dense dust clouds where stars are being born, and it can see light from the very first stars and galaxies that formed just a few 100 million years after the Big Bang. It is our new, most powerful time machine.
And we don't just use light anymore, we also listen. Radio astronomy.
Right. The visible universe is just one sliver of the story. The universe is also glowing with radio waves. Giant dishes like the Very Large Array in New Mexico listen to the hiss of cold hydrogen gas between the stars and the sharp beeps of pulsars and the violent jets shooting out of distant black holes. It's a whole other invisible universe.
So we've covered thousands of years of history, the physics of stars, the exploration of our solar system. Let's try to land this ship, the outro, the scale of it all.
It really is the classic powers of 10 exercise. You start with yourself here on Earth. You zoom out, you see the solar system. You keep going, you see the Oort cloud of comets surrounding it. You zoom out further, you're in the Orion arm of our Milky Way galaxy. Then you see the whole galaxy, a spiral of 200 billion stars.
But that's just our home.
It's just one galaxy in the local group, which has about 50 galaxies, including Andromeda. The local group is on the outskirts of the Virgo supercluster. And that supercluster is just one small lobe, an even bigger structure called Laniakea, a network of 100,000 galaxies. And Laniakea is just one thread in the cosmic web of filaments and voids that makes up the large-scale structure of the cosmos.
The observable universe is 93 billion light-years across. And that's just the part that light has had time to reach us from since the Big Bang.
It has a way of making our daily problems feel appropriately small.
The source ends with that haunting thought we touched on at the very beginning, gazing at remote galaxies. We can only wonder if there's someone on a planet orbiting one of his stars looking back at us.
And this brings us back to the time machine concept. If there is an advanced alien civilization in the Andromeda galaxy, 2.5 million light years away, and they look at our galaxy right now with the super telescope, they don't see us. They don't see our cities or our satellites. They see the Milky Way as it was 2.5 million years ago. They see the dawn of the human species, our distant ancestors walking on the plains of Africa.
And if they're even further out?
A galaxy 65 million light years away would see the dinosaurs. A galaxy 4.5 billion light years away would see a cloud of gas and dust just beginning to collapse to form our sun and Earth. We are cosmic ghosts to each other across the vast distances.
So the ultimate question, are we alone?
We don't know. That might be the most important scientific question there is. We are listening for signals with projects like SETI. We are hunting for the chemical biosignatures of life in the atmospheres of exoplanets with the James Webb Telescope. But for now, as far as we know, in this vast, cold, beautiful, expanding universe, we are the only ones asking the question.
Which in a way makes us pretty special.
I think it does. It makes us the consciousness of the cosmos for now. We are the universe waking up and starting to figure itself out.
I love that, the universe waking up. So, to you, our listener, tonight, if you can, go outside, find Orion, find that fuzzy little patch in his sword. And remember, you aren't just looking at lights, you are looking at the past. You are looking at the engines of creation that made you. And you are using the original scientific instrument, your own eyes.
Keep looking up.
Thanks for diving deep with us. We'll see you next time.